different operating regions of MOS transistor. One, subthreshold region. Two, strong inversion region. Inside that we have linear region and saturation region. Subthreshold region, the name suggests, we are below the threshold voltage, so the gate to source voltage is lesser than the threshold voltage. The threshold voltage is specific for a certain technology. Here the gate to source voltage we are applying is a positive voltage, and it is lesser than the threshold voltage. Hence the gate has positive charges which has accumulated in it. Because of the positive charges in the P substrate are repelled, which is seen here, and we are left with the boron ions, which are fixed atoms which has gained an electron. Hence the channel is free of charge carriers, and hence the depletion region is formed. And when we apply any voltage, that is drain to source voltage, the drain current is 0. Next is strong inversion region. Here the gate to source voltage applied is greater than the threshold voltage. The gate to source voltage is a positive voltage, and the gate is highly positively charged. The positive charges on the gate repels the positive charges of the P substrate, and it attracts the minority charge carriers, that is electrons, present in the P substrate, forming a channel over here. This region is called as an inversion region or an inversion layer, because we have inverted the polarity of charges under the gate from positive to negative. And when we apply drain to source voltage, the current flows. So when we apply drain to source voltage, we see current flow because of this channel formed. Saturation region, the gate to source voltage is greater than the threshold voltage. Channel is formed. The drain to source voltage is greater than the gate to source voltage minus UT. Solving this equation, we see that the gate to drain voltage is lesser than the threshold voltage. What does it mean? It means that near the drain we do not have channel, because the gate to drain voltage is lesser than the gate to drain voltage is lesser than the threshold voltage. So there is no inversion near the drain. How does the electron flow when there is no channel near the drain? Analogy is, if consider a bridge with an opening. If the car is fast, it can jump over the bridge and cross the opening. However, if the car is slow, it falls into the bridge. Here the electrons are fast enough such that it jumps over the no inversion region present near the drain. And here we have to remember the equation for drain current ID equals to beta naught n by 2 into W by L into UGS minus UT the whole square. Here the drain current, that is the output current, is proportional to UGS minus UT the whole square. Hence here it is not linear, and it is also not dependent on UDS voltage. Yep, let's see who is responsible for what. The gate to source voltage, that is the gate to source voltage, is responsible for forming the channel, since it is responsible for the charges present in the channel. And the drain to source voltage, UDS, is responsible for the flow of current. So UDS is responsible for flow of current. If we see this structure, this resembles a capacitor. Two parallel plates separated by a dielectric silicon oxide of thickness TOX, and the length of the plate is L, width of the plate is W, and the area equals to W into L. We know C equals to epsilon naught epsilon R, area divided by the distance between the plates, which results in epsilon naught W into L by TOX. We know Q equals to C into V. Therefore, Q equals to, that is the charges, equals to, substitute C in this equation, we get this, and the voltage applied is VGS minus VTH. So now we have the charges in the channel formed because of the gate to source voltage. For current, UDS is responsible. The UDS voltage generates electric field E, which is given by UDS divided by length of the channel. And because of the electric field, the electrons in the channel move at a speed called as drift velocity, Vd, which equals to the mobility of the electrons times the electric field. So the drift velocity Vd equals to minus mobility times electric field, that is Vds by L. We know the unit of drift velocity is meter per second. So we can write drift velocity also as the length of the channel divided by the time taken by the electrons to move across the channel. Therefore, the time t can be calculated from this equation as t equals to L square divided by mobility into VDS. So we have t, we have Q charges. We can write the equation for drain current ID, that is nothing but Q by T. Take the equations of Q, take the equation of T, divide each other, and we get drain current ID. Here in this equation, the designer cannot define the thickness of the silicon dioxide as well as the dielectric, the relative permittivity of the dielectric. Hence, this epsilon naught epsilon r into TOX is written as COX dash, and also we write mobility of the electrons cannot be decided, so we write together as beta ON. So drain current ID equals to mobility times COX dash times W by L into VGS minus VTH time into VDS. Inversion region, there are two modes of operation, that is linear and saturation. In linear region, the gate to source voltage is greater than the threshold voltage, and the drain to source voltage is lesser than the gate to source voltage minus the threshold voltage. What does that mean? Substitute UDS as the drain voltage minus the source voltage, and UGS as the gate voltage minus the source voltage. This cancels, and by rearranging the terms, we find that the gate to drain voltage is greater than the threshold voltage. That is, the gate to drain is greater than the threshold voltage. Hence, there is channel present near the drain, and obviously there is channel present near the source, since gate to source voltage is greater than the threshold voltage. So if you see this in a graph, this is gate to source voltage at the source, and at the drain it is gate to drain, and gate to drain is greater than the threshold voltage, but it is lesser than gate to source voltage by UDS. Therefore, near the source we have a bigger channel, and near the drain we have a smaller channel, since the gate to drain voltage is lesser than the gate to source voltage. And here we have to remember the equation of current, that is the drain current, which is equals to beta naught n W by L into UGS minus UTH minus UDS by 2 into UDS, where beta naught n is mobility into COX dash. COX dash is epsilon naught x by TOX. So beta naught n is a constant which the designer cannot decide, cannot choose, whereas W by L, UGS, UDS can be decided by the designer. Why is it called linear? Because if you see here, the drain current is linearly proportional to the gate to source voltage. The gate to source voltage is the input voltage, and ID is the output current. Because of this linearity, we call it as a linear region. The transistors are used in linear region for digital circuits, and when it is used as a switch. Summary of operating regions. Subthreshold region, UGS lesser than UTH, and drain current is 0 for any UDS voltage. Strong inversion region, UGS is greater than UTH, and in linear region, UDS is lesser than UGS minus UTH, which implies the gate to drain voltage is greater than the threshold voltage, and we get this current equation where UGS and ID are linearly proportional. In saturation region, UDS is greater than UGS minus UTH, which implies UGD is lesser than the threshold voltage. ID is proportional to UGS minus UTH the whole square, and ID is not dependent on UDS. Beta naught n equals to mobility times COX dash. COX dash equals to epsilon naught epsilon r by TOX.